Hey everyone, today we'll be diagonalizing a 3 by 3 matrix. Alright, so we have an equation that says A is equal to a matrix P, which consists of the eigenvectors of A, D, the diagonal matrix of A, times the inverse of P. And so what this lets us do is it lets us perform certain operations on A more easily, more straightforward. Let's say A represents the change of a subset of a population of a city that moves to another city over time. So let's say population from city 1 will move to city 2. The percent will be described by matrix A over the course of 1 year. Now let's say we want to do over 5 years, over 10 years. Well, over 5 years, it would just actually be matrix A to the fifth power. Problem is, if we try to do A to the fifth power, it's complex, it's messy. So A, P, D, P inverse lets us do it in a more straightforward way. By showing and saying that A to the 5 is equal to P, D, P inverse times P, D, P inverse times P, D, P inverse, and so on, 5 times, we see that these inner p's will all end up canceling out. P inverse times P, we know that's just the identity matrix. Any matrix times its inverse is just the identity. And so these won't actually do anything. They just go away. They cancel out, basically. And what we're left with is the first P times D to the n, which in this case is 5, times the final P inverse. And so this is much more simple to work with. The diagonal matrix is just the diagonal entries. So if we raise that to the fifth power, it's just the diagonal entries raised to the fifth power. Super simple, so let's get into it. First things first, we need to find the eigenvalues of matrix A. Now, the eigenvalues in this case, we see this is a upper triangular matrix, and so we know these eigenvalues are just going to be the diagonal entries. So we have lambda 1 is equal to 2, lambda 2 is equal to 3, and lambda 3 is equal to 1. Alright, so now we need to find the eigenvectors so that we can build P. So the eigenvector that will correspond to lambda 1 will just be A minus lambda 1 on the diagonal. And so we'll get 0, 0, 0, 1, 1, 0, 4, 0, negative 1 times V1. Set that equal to 0, and now we need to solve this. So with some row reduction, I'll move the second row up to the first row and then subtract that from the second row, and then that'll give us 1, 1, 0, 0, 0, 0. And then if we do 4 times the first row, subtract that from the last row, we get 0, negative 4, negative 1, V1. And so from this we have x plus y is equal to 0. Y is the free variable because the middle row is full of all zeros, so we'll just set that to whatever we want. I'll set it to 1. Since y is 1, it follows that x is negative 1. And then we have negative 4y plus minus z is equal to 0. And so this will just turn out to be z is equal to negative 4. So our vector 1 is equal to x is negative 1, y is 1, and z is negative 4. Now for the sake of time, I've already gone ahead and solved the other two eigenvectors, as this can be a little bit tedious and basically the same process solved all over again. So we get v2 I have is 0, 1, 0, and v3 is equal to 0, 0, 1. Alright, so putting this together in the correct order, we have P is equal to negative 1, 1, negative 4, 0, 1, 0, 0, 0, 1. Alright, so now we need to find P inverse. Well, we know that P inverse is actually the determinant of P under 1 times the transpose of P. Alright, so the determinant of P is just going to be negative 1 times 1 minus 0. So the determinant of P is actually just -1. And this is going to be times the transpose. Well, if we transpose P, we have -1, 0, 0, 1, 1, 0, and -4, 0, 1. And then multiplying that -1 in, it just flips all the signs. So 1, -1, 4, 0, -1, 0, 0, 0, -1. All right, and that's what we have. So our A, 2, 0, 0, 1, 3, 0, 4, 0, 1 times the D, which is just the diagonal entries of all the lambdas. So it's going to be 2, 3, 1, 0, 0, 0, 0, 0, 0 times the inverse, which is 1, -1, 4, 0, -1, 0, 0, 0, -1. So now if we want to do this to the power of 5, all we have to do is raise this D to the 5th power. So a to the 5 is just this P coming down times 2 to the 5th, 3 to the 5th, 1 to the 5th, 0, 0, 0, 0, times this P inverse coming down from there. And so that's how we do matrix diagonalization. This is how we would model the change of a population from one city to the next over the course of 5 years. Thank you so much.